Okay, it's my honor again to be back up here to present our next paper titled Resolution Alignment and Completeness System for Diagnosis Code Imputation, and this is in partnership with Ontotext. Okay, so just to give you a little bit of background, this project broadly is focused on democratizing patient data where patients take ownership of their own healthcare records. And so, from personal experience, God forbid you come from Netherlands to Barcelona, something happens, you have to go to the doctor, emergency room here. Your chances are very low that they will have access to your health records. And we're trying to kind of address this broader problem. And the lay of the land currently is these kind of what we call like knowledge silos, where, at least in Netherlands, your GP or your doctor has your records, maybe connected to some labs and hospitals. But more broadly, these are all in kind of disjoint, and we apply knowledge graphs to kind of integrate these and make these interoperable where the data is heavily heterogeneous across the board. So just to give you an idea, so you might have typical data EHR in each EHR cases, such as doctor notes, tables, lab results, images, and just to show you an idea about the issues, to us, maybe we quickly recognize those are all the same Dr. Smith, but it's when we're making interoperable systems, this becomes a challenge. Same thing for dates, units. Some really nice tutorials again yesterday focused on these. So hopefully you recognize these heterogeneous data issues. And give you, again, in Dutch language or any other language, this kind of escalates, and you will have all kinds of documented, specifically, let's say in this scope of this paper, looking at tabular EHR, you will have these undocumented tables, metadata may be missing, some logic or transformation on the data values are not clear. So this is kind of the situation when we want to take a typical data source and load it or integrate it into our system. So we proposed this modularly designed rack DCI system. And so I will go over the specific modules, and it starts with retrieval and parsing. And then again, we go back to embeddings, and then we do alignment with a target reference ontology. And then finally, in this specific case, we're trying to predict for missing codes, diagnosis codes in the data. For example, in the columns that you saw, there's codes that are missing, and we want to use the context to do that. So again, across the top, I'm showing the kind of linear pipeline. We have tables. Use ontologies such as SPHN to map in terms of schema, and then we end up with a knowledge graph, and then we embed those using different embedding models, and we perform a prediction task to impute missing data. In this specific case, we are focused on clinical ICD 10 ICD codes, and to thank the organizers and I think in timing these talks. And then we find that actually by aligning these using the mappings you saw previous speaker, this helps for our task of code imputation. So I'll have some results to show about that. So looking into the modules now, starting with DCA, which is data to some schema alignment. So this is kind of the previous work that we published, and it's available. So we call it annotation, but it's basically taking tables and mapping them to a reference schema. So we retrieve concepts, we retrieve predicates, So you can see the columns and then the relation between columns. And we use LLM models to generate the final knowledge graph from that. So I thought maybe it's better to show the results following every module rather than stacking them. So this is kind of what it looks like. We're using mimic data, which is ICU or critical care data set, and we load those data. Some of you were there in the RDF craft tutorial yesterday, so that's kind of the idea. So then we use the reference SPHN ontology, and then our LLM produces the personal health knowledge graph. So what I'm showing down is the precision of the mappings that we verify using the LLM. It's one-shot to n-shot training. So we retrain the LLM model. And then I'm showing the accuracy for single concepts and then the predicates, the relation between the concepts. So after 5 shots, we achieved the performance that is acceptable through the pipeline. So then this was So this was the first module. The second module is embedding. So we embed those knowledge graphs. So I'm not going to get into the details of that because we use off-the-shelf like Rotate E and other models to do that. So I'm going back to the results from the so now we have the ontology, and then in our specific case, the mimic data is encoded with ICD codes. So now we use the embeddings to align them with the SNOMED, and previously you saw the issues that are there. We kind of take a more inclusive approach. We don't leave things out. We actually, for every node, if there is one to multiple mappings, or if there is kind of this ambiguity, we include that actually in the embedding space. And I already presented here, we apply the RGC and OM algorithm previously in the morning I discussed. So we find that actually by including the full membership classes, so we see that that helps actually, at least in our pipeline. In the table here, I'm showing if we include single match or even, and also the one-to-many matches. If we include them, and between the, from left, I'm showing ICD-9 to SNOMED precisions, and on that side, I guess you're right, is on ICD-10 to SNOMED mappings, and in either case, we see that inclusion of broader mappings helps at least in embedding-based accurate mapping task. Again, so this again, we're step by step. Our hope is that we get above 90% or so accuracy, and we achieve that in the second module. And then, yeah, overall, when we put everything to the architecture or the framework I presented here, this is the overall results, and I kind of skipped over the embedding part, but in this paper we're using just translational embedding models like trans-E, rotate-E, torus-E. So, and for different kg sizes, if you like, with 100 patients, 200 patients, all the way to 500 patients. And then the columns are showing the NDCG accuracy. This is the cumulative gain, where it's a ranking metric in retrieval tasks. So NDCG at 1 and NDCG at 10. And then you see 3 sets of results. One is if we don't apply any of the modules that I showed. The middle is if we do without mapping to SNOMED, and the RAC is with alignment. The A is alignment with SNOMED that we found really enriches at least for our target application. So yeah, so we see that compared to without any of those modules, we achieve a lot of gain. And at least in NDCG at 10, those are acceptable up to, using also, depends on the embedding model, but torus E, for example, is with across all the modules, achieves the results we're hoping for. And yeah, the details, of course, I ask you to see in the paper. And then again, one last use case that we have that we wanted to solve was this. We have these patient data. These are anonymized, and then we have the diagnosis, concepts, labs, drugs, everything that were mapped to SPHN. So the blue is the SPHN overarching schema. And then again, I'm showing the predictions that for a given diagnosis or for a given patient here, for example, this diagnosis was missing, but given all the other context, some lab results, for example, we see that it helps us to kind of, if this certain diagnosis code was missing, we can predict and fill in the data hole. Yeah, so we proposed a modular system here called RAC, and with that it's a neurosymbolic architecture, and we can optimize each module, and we can add other modules to it, and then this really helped us, at least for the task of diagnosis prediction. It really helped us for imputing those missing data, and we hope to extend this for drugs, procedures, other missing parts in the data, and even do an integrated, maybe even, as I'm showing in the corner, with just using context embeddings and doing actual, clinical decision-making support. Thank you very much.
Thank you very much for your very interesting talk. When you generate RDF data from the tables, do you have any agents for the validation of the structure and also the content after the LLM?
I do, and it's in the paper. I didn't have time to include that. We checked the constraint satisfaction, so thank you for asking that. Yes, it's in the paper. In 10 minutes, I didn't have time to cover all of that. Thank you very much.
Very quick question. As a Dutch university, how come you're using the Swiss personalized health network ontology?
Short answer, because they were here last year and we used them. We used their schema, but yeah, if there are multiple choices for the ontology, and it's not in this work, and I've done actually studies to see the effect of schema, but yeah, we would love to also expand on the schema matching. The role of the schema with other ontologies related to particular regions or locations. Thank you. Yeah.